In this lesson, we're going to talk about an application of factoring, which would be simplifying by factoring. We saw an example similar to this when we were talking about greatest common factor. We have a binomial that's in common with each of the parts, that x minus 5. So we would say that we have a greatest common factor of x minus 5 that we could take out. And what we said to do was either you can see it visually and pull out that greatest common factor of x minus 5 in your head, or if not, then we said to actually divide each piece by that common factor of x minus 5. Because then what happens is that in terms of your answer, we're going to have that factor of x minus 5, and then we determine what we have after we divide it out. So x minus 5 divided by x minus 5, those will cancel out, leaving the 4x part. And then for our second part, again, the x minus 5s will end up canceling out, and we're left with just a positive 7. And that gives us our completely factored form, which another way to call this, it would be simplifying by factoring. So now we have an expression that's a little bit more complicated. We can see that we have multiple factors that are going to become our greatest common factor. We can see that this is not completely simplified yet because we have this plus in between. That means that it's not fully factored, but we can see that we have each part of 4 times x minus 1 to the third, x plus 3 to the ninth, and then 9 times x minus 1 to the fourth, x plus 3 to the eighth. So we still want to look for a greatest common factor between each of these two parts. So first, we want to look at our numbers, our coefficients, which would just be the 4 and the 9. The question would be, do we have a greatest common factor between 4 and 9? We don't, so then we keep going. Next, we look at their common factors. So one piece they have in common would be the x minus 1. We can see in our first group that we have an x minus 1 to the third, and our second group we have an x minus 1 to the fourth. Well, recall back to when we were doing greatest common factor with variables. When we had like bases, we would take the smaller power. The same is true here. When we have like factors, we're going to take the smallest power as part of our greatest common factor. So if x minus 1 to the third and x minus 1 to the fourth, we can see that x minus 1 is in common, but even more, we're going to take out an x minus 1 to the third, since the third is the smaller of the two powers. Continuing on to the x plus 3, we have x plus 3 to the ninth in the first group and x plus 3 to the eighth in the second group. Again, we can see that x plus 3 is going to be part of our greatest common factor, but we need to figure out the power to take out. Again, you're going to take your smaller of your two powers. So in the first group, we have x plus 3 to the ninth. In the second group, we have x plus 3 to the eighth. So we're going to be taking out an x plus 3 to the eighth, since that is our smaller power. So once we identify what our greatest common factor is, we do want to factor that out. And remember, when we factor it out, we want to divide the greatest common factor by each part. So again, you can do this in your head if you want to, but I'm going to show the division so that way we can see what the simplified form looks like. So I'm dividing each part by our greatest common factor, which is that x minus 1 to the third and x plus 3 to the eighth. And then same thing on the other ones, we have x minus 1 to the third and x plus 3 to the eighth. So remember that x minus 1 to the third and the x plus 3 to the eighth is part of our greatest common factor, so it's going to be on the outside of our final answer. So it's going to be inside, which I'm using with a square bracket. It's going to be what's left after we do the division. So in our first grouping, the 4 is going to stay since there's no number to divide out from our greatest common factor, so we're going to keep the 4. But then the x minus 1 to the third and the x minus 1 to the third will cancel out completely. The x plus 3 to the ninth and the x plus 3 to the eighth, since they have the same base, you're going to subtract your exponents again. Well, 9 minus 8 is 1, which means what we're left with is that same base, x plus 3 to the first power, which remember is really just x plus 3. Same thing's going to happen with our next grouping. That 9 will stay since we don't have a number dividing out on the bottom. The x minus 1 to the fourth divided by x minus 1 to the third, again, you're going to subtract your exponents since they have the same base. So 4 minus 3 is 1, which means this is going to be left with x minus 1 to the first, which again is just x minus 1. X plus 3 to the eighth and x plus 3 to the eighth will cancel out completely. So inside the square brackets here is what's left after we factor out the greatest common factor. So you don't need to show that step of the division, but you need to understand what's happening is that you're dividing out, and if you have the same base, you're going to subtract your exponents. Our next step then is to simplify what's left inside of our square brackets. So our greatest common factor of the x minus 1 to the third, x plus 3 to the eighth will stay. Inside x plus 1 to the, x plus 3 to the first is the same thing as x plus 3, which means that we can distribute the 4. So that makes this 4x plus 12. Then plus distribute the 9, you're going to end up with 9x minus 9. Continuing to simplify inside, we can combine like terms, so we have that x minus 1 to the third stays, x plus 3 to the eighth stays, and then inside 4x and 9x would end up being 13x. And then 12 minus 9 would be 3. So this would be our fully factored form, or the original expression simplified by factoring, since we have 3 factors shown through multiplication. You can use the square brackets here at the end, or you can use parentheses.